One of the most frequently asked questions of budding game developers wanting to make visually attractive games is how to make lighting. Defold allows you to totally redefine your render pipeline, and so you are able to create a lot of different lighting implementations. So let me help you understand how to make simplest 2D lighting in Defold. And even if you are not a Defold user, it is generic enough to learn how render targets and post-processing works in game development. Straightforward way of rendering is to draw everything directly on a buffer that is immediately displayed on a screen. We can of course modify each visual object's shaders to modify how vertices are placed or how fragments are colored, but if we would like, for example, to make a whole game in grayscale or with post-processing like in the Return of the Obra Dinn, we would rather more naturally apply such effect to a whole frame than every single object separately. To make full-screen post-processing, we usually draw our whole frame not into screen immediately, but into some internal place, a buffer, or better said, a render target. In Unity, it is also sometimes referred to as render texture. Both are good descriptions of what it is: a target to which we would like to draw, a separate texture, a canva, internally stored in a graphics card and not yet drawn on a screen, so we could perform further processing of such texture before actually putting it on display. I'm a 2D guy, you know, but utilizing render targets you can achieve amazing post-processing and lighting effects in 3D games as well, and create different implementations like deferred lighting or physically based rendering. So if we want custom post-processing or lighting in Unity or Defold, it is obviously possible to do it without built-in light components. Unity and Defold also utilize drawing to multiple render targets at once, which reduces the amount of drawing operations, so-called draw calls, which are most costly in our update functions, and therefore multiple render targets are commonly used in deferred lighting implementations. Drawing to render targets enables us to make very complicated and simple post-processing effects, like for example desaturating all the colors of our frame and making everything in grayscale or blurred or with inverted colors, or adding some other visual effects to the whole frame before drawing it on screen. The simple lighting effect idea is very straightforward. Draw everything, our sprites, backgrounds as usual, but on a separate render target. Then draw additional light volumes, a visual representation of lights, to another separate render target. This approach I like to call light maps, because when we draw this second render target onto our screen directly, it is simply this, a map of lights. And because we are applying lighting to only what's visible in the finale of the render process, so in our screen space, I call it screen space light maps. Having two such textures, we need something where we could blend them together, a separate model or a mesh or anything to which we could assign a texture and draw it then to the screen. In Defold, I use a simple built-in quadratic plane model which can take multiple textures in its material, and I could blend them in its fragment shader, which takes colors from both textures at each given fragment and only multiplies their values, giving you a blended picture with which we fill the screen then. This is tricky to achieve, but in previous videos I explained how the default render script works and teased the use of render targets. So let's implement something like this together. You can start with your own game you want to light up. Everything should stay the same, and we will add another layer on top of this. I have here a simple mockup with pixel art from a game I'm working on. Nothing special, just sprites. But we add the layer with lights forming our light map on top of our mockup. The map consists of sprites representing circular white lights with decreasing transparency from center to the edges. We need to create separate materials for them. We can copy the default sprites material with its shaders, vertex and fragment program. But we need to change the tag for creating a separate predicate for them. Let's call it light. When you change the material for all sprites, you will notice they are no longer rendered in our game, because we do not draw such predicates in the default render script. So now to rendering. We can start with the built-in render script. You might already use render scripts provided by popular default camera assets like orthographic or RenderCam, but they mainly modify how you see the world. So you might be able to easily add a chunk of code that we will add right now to the default script. copy the render file and the render script and assign our script to our render file. Don't forget to also change the render file in game.project and then open our render script. We will draw our world separately from the light maps, so we'll enable the first render target using render.setRenderTarget function. Then we will draw the actual game world as usual here and get back to the default render target in the end. For convenience and to quickly understand what is going on, we will wrap it up in a function called render_to_render_target, which will take as parameters the render target and the drawing function callback. We also need to create this render target. So create it in our init function using render.renderTarget function and specify its name and parameters. For now, create the color parameters like here with RGBA format, window width and height, linear filtering and UV wrapping using clamp to edge methods. You can check the details of those parameters later on. Assign created color parameters to the color buffer of our render target. We also can now add a second render target with the same parameters, but with the name lights, that we will be using to draw our light maps. We don't need to change anything in the drawing process, so it starts as usual with clearing the current buffer and setting up the view and projection that we have defined earlier on. We need to set the proper renderer state and set up masks as usual. We could also clean and avoid duplicates here, so wrap it in some convenience functions. First one to clear the current buffer with given color, and second to set commonly used renderer state. Then draw our world objects predicates. And again add another function to draw to the second render target and repeat all the stuff we did inside. But this time change the predicates drawn here to draw lights only and maybe modify the color which is used to clear this buffer, because we would like to set some ambient lighting, so when we clear the buffer with this color and then draw lights on it, the whole texture will be visually tinted with the ambient color. Right now we draw to two separate targets, but not to screen anymore, and at this point I remember how frustrating it was when I was learning it, because I saw black screen and thought I did something wrong. Let me show you that it's not true and we did draw everything, but into an internal buffer. We can now take those internal buffers as textures for the quad model on which we will draw everything and fill the screen with it. Add the quad model to our collection utilizing the built-in quad mesh and create a new material for it. You can again copy the built-in model material, rename it, open and assign copied shaders to it. Change also the tag to quad to draw it separately at the end of our render pipeline. And because this model will use two textures, our render targets, add an additional texture sampler in Fragment constants. This will allow us to assign a second texture to the model. Now modify the Fragment program. If it is your first time modifying a shader, Defold uses GLSL, which stands for OpenGL Shading Language, which has a syntax based on C programming language. But don't worry, we will only make very basic, easy to follow modifications. The Fragment program is simply calculating output colors for each of the pixels simultaneously, so there is only one function called main that is called for each pixel. The output color is saved to a special variable called glFragColor. For clarity, remove everything from here except this last line and assign a simple color to output instead to see if we make everything correctly. If we pass here only one vector representing, for example, red color, we will see the whole screen filled with red pixels. We will get back to this shader later on, but for now open our render file and add our material to the list here, with a proper name, for example, lighting quad. Below the code where we draw to render targets, we will be drawing to our quad plane. Set now view and projection to identity matrices to fill the whole quad. And set our usual renderer state. Now enable a material we defined in our render file and called lighting quad. The material we imagined will be used to draw quads, which we will for now fill with red pixels as you remember. While using this material, enable two textures corresponding to our render targets and assign them separate consecutive texture unit numbers to distinguish them. And finally draw our quad predicate. And one last thing before drawing our GUI, fold back our textures and material by disabling them. That's all, and if everything is correct, when we run the game we should see a red filled window. Okay, so get back to our Fragment program of lighting quad material, and instead of the red color, get the color from the first texture, our render target representing the game world, using texture2D function, which will get the current pixel color of the provided texture sampler. This texture sampler is available here as a uniform, low precision constant of type sampler2D and named text0. Name must be the same as defined in material constants. Beside the texture itself, we need to specify which point on the texture we are actually sampling, and utilize the fragments coordinates here, defined in a varying medium precision value of type vector2, named var text chord 0, which internally we get from vertex program. You can also multiply this color by a tint constant, but it's not required here, so we'll skip this. Now, instead of our red color, put a color from our texture sampler to the output and see the result. On a quad that fills the screen, we see a texture to which we draw our game words. So let's add lighting now. The trick is to simply modify the fragment shader and get a light color for a given fragment from the second render target, where we draw our light maps the same way as we sampled the word texture. At the end, multiply the two colors in the output and see the result. We made a very simple lighting implementation with a good enough understanding on how to utilize render targets to create post-processing effects in Defold. If you want to dig in further for some other effects, leave a comment below. Have a fruitful day and happy defolding!